In this video, we will talk about path integrals of both scalar and vector functions. This video does depend on you knowing about parameterized paths, sigma, which we had talked about something like 3 chapters ago, probably chapter 3 in your book. I will do an extremely cursory, brief review of parameterized paths, but you might want to make sure you're solid on that subject. Additionally, this subject of path integrals will show up from now until the end of your book. So it behooves you to become familiar with this and learn this well now. It'll really serve you throughout the rest of this class. There is the second summary page, which we will go over. Once we have gone over the 2 summary pages, I'll have some examples for you, and then for review, I have a couple of problems for you to try. First, we will do a quick review of the overview slides before going into each topic in more detail, and I have a lot of examples for you. So again, we're going to talk about path integrals of scalar and vector functions. Scalar functions will denote with a lowercase f. A vector function we will denote with an uppercase f. Something else that's good to note now is for path integrals, these have a lowercase s. Later we'll be doing surface integrals, those will be with uppercase, so it's good that you know what's being asked of you. If there's a lowercase s, it's a path integral. Also, if you try to plug a surface into here, like the formulas won't make sense. But anyway, the steps for both the scalar and the vector path integrals are very similar. The first step is you parameterize your path sigma. Second, you write f or your scalar function or your vector function in terms of the path. In other words, you use function composition. Third, you take the derivative of the path. And fourth, you plug in all these components into your formula. So a quick example of how this works for a scalar function. So if our path is the helix, sort of like this drawing here, where we have the circles cosine t, sine t, and the t means the circles are rising. So this is our parameterization of the path, and we want to integrate this scalar function, x squared plus y squared plus z squared, over this path. Then the first step is to parameterize the path, and in this case, it's already been done for us. The second step is to write f in terms of our path. In other words, use function composition. So we want our f composed of sigma and prime. In other words, f, I'm going to plug in my sigma, cosine t, sine t, and t. When I plug these into f, I'm going to have x squared, which is cosine squared. And then the next term of my f is y squared. That will be sine squared. And then finally, I have z squared, which is t squared. So that will give me 1 plus t squared. The next step is take the derivative of the path. And for scalar functions, which we have, we want to find the magnitude of the derivative. So taking the derivative of the path just term by term, our path is here. Derivative of cosine is negative sine, derivative of sine is cosine, derivative of t is 1. And then taking the magnitude, we get square root of 2. And then step 4, I'm going to plug it into my formula for the scalar function. So we go from a to b, and here a to b is given to us when we parameterize. So we're going from 0 to 2 pi, and then we're going to have our function composed with our path. That was over here. So that'll be our 1 plus t squared, and we're going to multiply it by the magnitude of our derivative, which is square root of 2. And then you solve this integral and you get your solution. To show you how this works for the vector function, let's say then same path, and our vector function, f of xyz, is simply xyz. So it takes a vector, you get the same vector back. As I said, step 1 has already been done for us. The path is right here, over here. Step 2, f composed of t. So f, we're going to plug in sigma of t, sine t, cosine t, and t. Plugging into f. So first we put in x, which is just sine t, we plug in y, which is cosine t, and z, which is t. So again, this function isn't that creative. It just takes xyz and gives you back xyz. Step 3 is to take the derivative of the path. So sigma prime of t, so where's sigma? Here's sigma. So derivative of sine of t is cosine, derivative of cosine is negative sine, derivative of t is 1. And then last, plug into the integral. So we're going to integrate So we're going to integrate from a to b, and our parameterization tells us that a is equal to 0 and b is equal to 2 pi. So we integrate from 0 to 2 pi. Then f composed of sigma, which is equal to sine t, cosine t, t. And then we dot that with the derivative of the velocity of sigma prime. So that'll be cosine minus sine t and 1. We do the dot product, we do the integration, and we get our solution. We will also talk about reparameterizing paths, and that is this line integral. It depends not only on the field f, but also on the path. And in general, two different paths, sigma 1 and sigma 2, will yield two different values for the line integral. But if the path integral is the same with a possible change of sign, then that is called, sigma 1 and sigma 2 are called reparameterizations of the path. So one reparameterization is the sigma opposite, which is orientation reversing. So let's look at this helix back up here. Currently, our parameterization in time goes up the helix. But if we use this different substitution, what we would get is the opposite orientation where we're coming down the helix. We'll see an example of this later. But we also have this theorem that says if f is a vector field continuous on the C1 path, sigma going from A1, B1, and R3, and let's have another path, this rho, going from A to B to R3, and it's a reparameterization of sigma. So if rho is orientation preserving, then our line integrals should be equal. If rho is orientation reversing, then rho is just the negative of the line integral using sigma. So in other words, if you have one parameterization of a curve going up, like on this helix, going up on the helix, and you take a line integral of some vector field f or some scalar field little f, then if you parameterize the path going backwards, your line integral will give you the same answer. It'll just have a negative in front of it. We'll go over some other examples of reparameterizations of paths, and then finally we'll talk about the physical interpretation of a path integral, and in physics, that would be the work done by your force F moving a particle along your path. So work done by a force moving a particle along the path, that's what your path integral is about. We have these alternative formulas, which we'll talk about more, and there's another third alternative form. So that's kind of an overview of what we're going to do. So now we'll look at each topic in more depth, and then we'll follow up with a bunch of examples. Before we get too much into the integrals, I am going to give you an extremely brief reminder about paths, and it's nowhere near the amount of stuff that you should know, but this is how we're going to start this video. So the idea of a path sigma is that given some variable, such as t, which we often think of as time, over time, we'll be tracing out some path in space, in this case in 2 dimensions. And so given a single variable t, we're going to be giving you an x-coordinate and a y-coordinate. So your x-coordinate is dependent on t as well as your y-coordinate. If I plot out different points, and I'm so bad at knowing my sines and cosines, but if I did plot out, 0, actually I can do that one. I can do pi over 2, I can do pi, and I can do 3 pi over 4, but all the stuff in between, I don't know. But if you plotted all of them out, you'd see you would get a circle. So this path is a circle parameterized by this sigma going cosine t, sine t, t goes between 0 and 2 pi. You can further verify that this is a circle because if you add the x-coordinate plus the y-coordinate, that would be cosine squared t, sine squared t, you would get equal to 1. So essentially, this is the equation of a circle of radius 1. Similarly, I have this parameterization where sigma of t is equal to t and t squared. So here I did write out some simple values for t, and then t and t squared, or x and y, and I plotted them, and I see that I get this parabola. And this parabola makes a lot of sense. The relation is actually equal to y here is actually x squared. So this parameterization is exactly this equation. That's it for this very cursory review. The other quick thing I want to mention, because you can see here I have a formula for scalar functions and a different formula for vector functions. They're very similar, but they are different. So I want to make sure you know the difference between a scalar function and a vector function. So a scalar function maps multiple variables. So in this case, I have x, y, z to a single real number. It does not map to a vector because it has no direction. It's just a single real number. So for example, if I have f of 1, 2, 3, and I plug it into this function, I'm going to get my 1 times 2 times 3 squared plus 2 times 3, and I get 30. So 30 is a number. Whereas if I have this vector function, which looks very similar, not quite the same, but similar, now when I plug in 1, 2, 3, I am going to get 1 times 2 times 3 squared, which is 9, is 18 for my x coordinate. For my y coordinate, I'm going to get 2 times 2 times 3, that's 12, and then for my z coordinate, I'm going to get 0. So here, my vector function produces a vector. So this is exactly what it sounds like. My scalar function produces a scalar, my vector function produces a vector. And it's important to keep those straight. And the other very important thing to notice is by convention, my scalar functions have a lowercase f, whereas my vector functions are denoted with an uppercase f. So the uppercase means it's a vector field. You produce a vector. The lowercase means it's a scalar. And it would not be incorrect to write a vector field with a lowercase f because it is a function, but by convention, it should be an uppercase. Before we go on, I do want to say something about notation. Here in my ds, this should be a lowercase s. I tried to make it look like a lowercase, and it's important because later when we do surface integrals, those will be designated with a capital S. Capital S for surface, lowercase s for these path line integrals. So it's important you notice that, because if you don't, you'll be calculating the wrong integral. And actually, it probably won't even make sense, and then it'll be really confusing because you can't plug a surface into here when you're looking for a path. But to avoid confusion in the future, remember this lowercase s designates the path integral, and that is an important distinction. Also here, in this vector form, there's a dot here. That designates the dot product. It's kind of hard to see, but there is a dot. We are going to learn to take the path integral both for scalar functions and vector functions, and the steps to do those are very similar. The first is to parameterize the path. The second is to write f or a capital F in terms of the path, that is, use function composition. Third, take the derivative of the path. This is really the only difference between scalar and vector. For scalar functions, find the magnitude of the derivative, and then fourth, plug into the formula, the integral formula. And of course, the formulas are a little bit different, but not by much. It's either just a multiplication or a dot product. The other thing to note is when f equals 1 in this scalar function, we're simply restating the definition of the arc length of sigma. We'll start with this example. So we have sigma is our helix, which we've seen a few times now, and it's parameterized by t. It could have been theta, but it's parameterized by t in this example. T goes between 0 and 2 pi, and we map from t to cosine t, sine t, and t. The function we're going to integrate over this helix is a scalar function, f of xy equals x squared plus y squared plus z squared. So let's look. First step, parameterize the path. And actually, that's already been done for us. So sigma t is equal to cosine t, sine t, and t. The second step, write f in terms of the path using function composition. So here is our f of sigma of t. So sigma of t, I'm just going to plug that in. We have f of cosine t, sine t, and t. So plugging in cosine, sine, and t into f, which is given to us here, will be cosine squared, our y squared will be sine squared, and then z squared will give us our t squared, which will simplify to 1 plus t squared. Step 3 is take the derivative of the path. And for scalar functions, which we have, we're going to find the magnitude of the derivative. So sigma prime of t, here's our sigma, is going to be derivative of cosine is negative sine, derivative of sine is cosine, derivative of t is 1. And the magnitude of this is the square root of sine squared, cosine squared, 1 squared, which is square root of 2. And finally, we can plug in all of our components into our integral. So where is our formula for our integral? It's over here. So a to b, and that's given here, 0 to 2 pi, then f composed of sigma, which is 1 plus t squared, and then the derivative of sigma, which is square root of 2. So square root of 2. So I take, I do the integral, and this is my final answer. One other point I wanted to mention is this f composed of sigma of t. The reason why we do f composed of sigma of t is that f here it'll assign values anywhere in the x, y, z, in 3 space, right? You plug in any x, y, and z. Maybe out here you can get some, at 100, 1,000 or something. You can get a value. It would be 100 squared plus 100 squared plus 1,000 squared. But we really don't care about the value everywhere in the space. We only care about the values on the helix, which is why we plug in our sigma into our f. So in other words, we're only interested in the t's that gives us points on this helix, which is we find those points by plugging in our sigma into f. And the idea is, remember, the physical interpretation of f, of this line integral, is its work done by f moving along a path. So we only care about the force that we need along the path. So that's what this function composition is about. Let's compare that to same sigma, sine t, cosine t, t goes between 0 and 2 pi. But now let's look at a vector function. We take the vector xyz and we spit out the vector xyz. It's sort of like an identity function. We want to compute the line integral of f over sigma. Our first step is to parameterize the path. Again, that's been done for us. So sigma of t is equal to sine t cosine t t. Our second step is to write f in terms of our path using function composition. So f composed of t, that's f composed of sigma t cosine t t. I just plug in sigma of t into f. So f is equal to x, y, z. So first we take x, which is sine of t, y, which is cosine t, and z, which is t. The third step is take the derivative of the path. So sigma prime of t, derivative of sine is cosine, derivative of cosine is negative sine, derivative of t is 1. And finally, we can plug into the integral. So here is the integral we're going to use. So a to b, integral from a to b. So a to b is given to us by our path. I really should have written that here. Our integral is given by our path. T goes from 0 to 2 pi. And then we're going to have f composed of sigma, which is here, sine t cosine t t, dotted with the derivative, dotted with cosine t minus sine t 1. So when we dot this, sine times cosine of t, plus cosine t times minus sine of t, plus 1 times, t times 1. So we take the integral and we get the final answer of 2 pi squared. We are going to do more examples, like many more examples, of path integrals of a scalar function and also of a vector function. But first we're going to also look at reparameterizations of a path so that we can also use those in an example. So the idea is the line integral depends not only on the field but also on the path. Obviously, you can see that in the formulas up here that they depend on the path. In general, 2 different paths, sigma 1 and sigma 2, will yield 2 different values for the line integral. But if the path integral is the same with the possible change of sign, then we call the 2 paths reparameterizations of each other. We kind of consider them the same path for all practical purposes. The first reparameterization we have is this sigma opposite, which reverses the orientation of the path. So looking back up here at our helix, if sigma goes in this positive direction and we're going up, rising up the helix, we could reparameterize using the sigma opposite, and then we would be traveling down the helix. So that's what this is right here, the orientation reversing. So this will be our first example that we'll go through. And also, I'm just going to mention this theorem. So if you have an orientation preserving, if rho and sigma are both line paths, and they have the same, they're basically reparameterization of each other, but rho is orientation preserving, same direction, goes in the same direction as sigma, then you expect their line integrals to be the same. If they're orientation reversing, then you expect their line integrals to differ only by a negative sign. So we're going to go through these examples of reparameterizations. I moved this reparameterization information up so that we would have more space, and the most common reparameterization that you'll find that you'll be using will be the opposite. So that's to reparameterize something so you go in the reverse direction. So C1 goes from 0 to 1, the reverse direction would go from 1 to 0. Same path, just opposite direction. If you have a circle traveling in the counterclockwise direction, the opposite direction will be in the clockwise direction. Sorry, this isn't a very good circle, but you get the idea. And just to show you how this works, so if C1, if we parameterize this path in the C1 direction, here we have y is equal to 0, and x can just follow along with t. If t goes from 0 to 1, we could just say x just follows from 0 to 1. So the opposite direction, to use this formula, we do a plus b, so our a is 0, b is 1, and then minus t, which just gives us 1 minus t to the 0. And then just to kind of plug in some points, just so you can see this, so for different values of t, 0, 1/4, 1/2, and 1, you can compare what the path looks like when you use parameterization for C1 versus C1 opposite. So at t equals 0, we get 0, 0, whereas opposite, we get 1, 0. So we're already kind of going in the right direction. This one's going to go this way, C1's going to go that way. When we have 1/4, we plug in, we get 1/4, 0. And then at 1/2, we get 1/2 here. And then we finally end up here. So we're definitely going in this direction from left to right. Whereas here you see we start at 1, 0. We plug this in and we get 3/4. So we're moving this way. And then 1/2, 0. So we're moving to the left until we finally get to 1, 0. Actually, that's not right. I subtracted wrong. If t is equal to 1, 1 minus t is 0. So 0, 1, which is exactly the direction we want to go. Compare that to the circle. So I just plugged in some easy points for t, 0, pi over 2, pi, and 3 pi over 2. We only need to get the direction. So when t is equal to 0, cosine of 0 is 1, sine of 0 is 0. Cosine of pi over 2 is 0. Cosine of pi over 2 sine of pi over 2 is 1. Cosine of pi, so we're over here, is equal to minus 1. Sine is 0. And then finally we have 0 minus 1. So you can definitely see we're going 1, 0, 0, 1, minus 1, 0, 0 minus 1. So you can see we're going in this counterclockwise direction. We can compare that to C opposite, which again we take a plus b, which is 0 plus 2 pi, minus t. So this is our reparameterization. So if we do cosine, in this case of 2 pi minus 0, we're going to get 1, because we're at cosine of 2 pi, which is 1, and then sine at 2 pi is 0. So we start here. Then we have pi over 2. So cosine of 2 pi minus pi over 2 is cosine of 3/2 pi. So 3/2 pi. So that'll give us 0 for cosine. And for sine at 3/2 pi, we get negative 1. And then cosine at 2 pi minus pi, that's cosine at pi, which is here, gives us the negative 1 at cosine and 0 at sine. And then finally 3 pi over 2 gives us 0, this point here, 0, 1. So you can see we're going now in the clockwise direction. So that's what this means by orientation reversing. We have just talked about this, the orientation reversing reparameterization. Here is a reparameterization of sigma that's orientation preserving. I will leave it to you to verify that, much the way we did this orientation reversing. So next we're going to look at this reparameterization, but I'm going to move some things, clear some things out and give us a little bit more space. In this next example, we have two paths. First, we have sigma parameterized as x equals cosine 2t, y equals sine 2t, where t goes between 0 and pi. And we are going to show this as a reparameterization of our second path. We'll call it rho, where x is equal to cosine t, y is equal to sine 2t, t goes between 0 and 2 pi. So same x, same y. It's the limits of t that is different. So let's start with this first sigma x is equal to cosine t, y is equal to sine 2t. So at t equals 0, we start off at the point 1, 0. And then as t progresses, oh, and I'm going to say I'm sorry, but I realized that if you just plot these 4 points, it would look like a diamond shape. But we know this is a circle, so forgive me and just kind of like go along with this. And then when t is equal to pi over 4, now cosine of 2t, so we have cosine of pi over 2, sine of pi over 2, so what we get is 0, 1. So at t equals pi over 4, we've progressed up to 0, 1. Skipping ahead, as t equals pi over 2, we're going to get to 0 minus 1. Where's 0 minus 1? It's way over here. And then finally, at t equals pi, so now we're going to have cosine 2 pi and sine of 2 pi, which is just 1, 0. So you can see between t equals 0 to pi, we've traversed the entire circle. Now I can look at my parameterization here where x is equal to cosine of t and y is equal to sine of t. So at t equals 0, I again start off at the point 1, 0. As I progress, t equals pi over 4, I get to this square root of 2 over 2, square root of 2 over 2. At t equals pi over 2, I'm going to get to 0, 1. Actually, I think I made this too high up. At t equals pi, I'm going to get negative 1, 0. X equals negative 1, 0. And then I just skipped ahead. When we're at t equals pi over 2, I'm going to come back around to 1, 0. So this is my circle. And you can see our two paths are the same. They're reparameterization. It's just that this one, in a sense, has made it there in half the time, right? So it only had to go to pi, whereas this, the time had to go to 2 pi. It's the same curve, just this is done in half the time. For our line integrals, which physically and talks about work done, they're the same. It's the same amount of work. It's just that this was done in a shorter amount of time. We have this next reparameterization, x equals cosine t, y equals sine t, where t goes between 0 and 4 pi. And we want to compare it to our x equals cosine t, y equals sine t, t goes from 0 to 2 pi. So we're comparing it against this parameterization. So I can start at t equals 0, and I start the same spot. I move on to t equals pi over 2, and I get to 0, 1. I then go on to t equals pi. I get my negative 1. My graph is a little bit off. So here, negative 1, 0. I'm at 2 pi. So I come back all the way around. So this is at 2 pi. But I need to keep going. When I'm at 2 pi plus pi over 2, I'm going to come back around again. So the second time, maybe I'll do this in blue. And then at 2 pi plus pi, I'm going to be at negative 1, 0. Do this in blue again. And then I'm just going to skip over 2 pi plus 2 pi. You know, we know it's periodic, so it's going to go around a second time. And this parameterization, we do not consider the same. It's not the same representation. Among other things, if you're doing work, like if you're running around a track, running around it twice is more work than running around it once, right? So there's more work involved in moving around this twice than moving around it once. So for this reason, this here is not considered, or this parameterization is not considered a reparameterization of this one here. It traces the same image, but it does so twice. It does twice as much work. And just to remind you, the physical interpretation of these path integrals, as I've sort of been referring to, is the work done by your force, F, moving a particle along the path sigma. There is this alternate form here. So you take your line integral formula, and this is for a vector function, capital F, so producing a vector, not the scalar functions. So you take your formula, you can divide by the magnitude of sigma prime. And then to keep it equal, you're going to have to multiply by the magnitude of sigma prime. So this might seem like a dumb thing to do. Why would you divide and then just multiply it out? You could just do this dot product and be done with it. And the reason is if you happen to know, this here emphasizes the fact that this is the tangent vector. The sigma, because it's your unit tangent. Basically, if you think of sigma, if you go back and think of the path, sigma gives you the position of something at time t, so the derivative gives you kind of the tangent, if you think of the derivative as a tangent. So this is the unit tangent. So what that tells you is, let's see, for paths that satisfy sigma prime of t not equal to 0, you can use this, but it also tells you that the integral depends on the tangential components of f. So in other words, if your movement and your force are directly perpendicular, there's going to be no tangential component, and it would be equal to 0. So this formula, if you know something about the tangent or the perpendicular or how f is in comparison to sigma, that's when this formula becomes handy. So we'll look at that on the next slide. So to talk about this, I kind of move this to a separate page so we have more room. So here we have a path, sigma, and we're going to say the direction of this path is kind of going upwards. So if f moves along, if it's tangent to the path, then you can see how f is going to help move any particle along this path. Whereas if f is perpendicular to sigma, then it's not going to do anything to help move the particle. So that's what this is about, this tangent form. So we only want the component of f that's tangent to the curve to count as, that's what contributes to our work done. And one other case, if f is tangent but in the opposite direction, then f is impeding the work, impeding movement along the path in the direction of the path. And your work done will be a negative number that indicates that f is impeding movement along the path. We have this third form of the line integral, for the vector functions, it's really fancy. It's got like 3 forms. But anyway, because you have a vector form, we can often write f, our function, in terms of f1 being the function that assigns the x-coordinate, f2 the function that assigns the y-coordinate, and f3 the function that assigns the y-coordinate. And then our line integral becomes over the integral over sigma f1 dx. This dx, that's the that's with respect to sigma. This refers to sigma, not f1, plus f2 dy of the sigma plus f3 dz. So in other words, I like this form a little better than this one because it's more explicit. We go from a to b, f1 dx dt plus f2 dy dt plus f3 dz dt of dt. And again, your hint that this dx, dy, and dz have to do with sigma is because it's of the dt underneath. And also this f1, f2, f3, you need to compose it with sigma as well. Just like, once you plug it into the integral, you need f composed with sigma. This next example is good practice in parameterizing a curve. Actually, it's not a curve, it's parameterizing lines. And also you see you have this vector form of f of your capital F. So we're going to rewrite that, or write our f of xy, then is going to be x squared y. Next, we're going to look at parameterizing the path. And to do this, I'm going to do this 2 ways for you. First, I'm going to do it the way I think is most intuitive and obvious, but there's another way of doing it. So I have broken it up into C1, C2, C3, and C4, and then I parameterized each of them totally independent of the other, and then I'm going to sum them up. So for C1, we can see that y is constant at 0. And now if t goes from 0 to 1, we can have x just follow along with t. It can go from 0 to 1. So our C1 is parameterized as t0. We can use kind of the same ideas to get the path for C2. So I see that x is held constant at 1, and y, well, if t is going from 0 to 1, then I can say that my y value just follows t. It goes from 0 to 1. I am going to do this a second way using a formula from chapter 1 when we talked about parameterizing an equation of a line through a particular point with a particular direction. So a line through this point and a line with the direction of the vector v. And the parameterization we used is our line of t is equal to our point plus t times v. Remember we talked about equation of a line requires a point and a direction, and we multiply the direction times t. We're going to use this for C2, illustrate for this for C2, just to illustrate it. And then this equation will become more important or more useful with more complicated type of line paths. So for C2, I see that I have the point 1, 0, and then my direction is in the positive y direction. In other words, it's in the direction of 0, 1. So this gives me my parameterization is equal to 1 plus t times 0, which is just 1, plus 0 plus t times 1, which is t. So you can see these two formulas agree. And again, C2 is easy enough to do intuitively, but we want to get used to this equation for more complicated lines. For C3, our point on the line is going to be this point here, 1, 1. And then we're going to multiply t times the direction. And the direction is in the negative x direction. So that will be minus 1, 0. So my parameterization for C3 is going to be equal to my 1 plus t times minus 1. So that's 1 minus t. And then we also have, for the y-coordinate, 1 times 0, which is just 1. And again, t goes between 0 and 1. And we can kind of give a little quick check. So when t is equal to 0, we have 1, 1. So we start here. And when t is equal to 1, we have 0, 1. So we end up here. For C4, C4 contains the point 0, 1. And it goes in the negative y direction. So the direction is going to be 0, minus 1, which means my sigma of t is going to be 0 plus 0t, which is 0. And then I have 1 plus t times minus 1. So it's 1 minus t. And again, my quick check would do, when t is 0, we're starting off at 0, 1. And when t is 1, we end up at 0, 0. Now that I have parameterized my path, I am ready to do step 2, which is to write my vector field in terms of my path. Again, we're not interested in all values of the vector fields, just those on the path, which is why we do the composition. So big F of plugging in t for x and 0 for y is equal to t squared, 0. For C2, I'm plugging in 1 for x and t for y, and I get 1 squared and t. For C3, I'm plugging in 1 minus t for x, 1 for y, and I have 1 minus t squared and 1. And then for C4, I have 0 and 1 minus t plugged in as 0 and 1 minus t. For step 3, I take the derivative of my path. I had to move this information over to make room for the derivatives. So for C1, the derivative of t0 is 1, 0. For C2, my derivative is 0, 1. For C3, my derivative is negative 1, 0. And for C4, it's 0, negative 1. Now we're at the last step, which is to plug into our interval. So our formula for a line integral with a vector field is to take the function composition f composed of our sigma dotted with the derivative of t. So it's essentially here, f composed of our sigma dotted with the derivative. So I've done that. For 0 to 1, I did t squared 0 dotted with 1, 0. And then again, for 0 to 1, 1t dotted with 0, 1. And then again, from 0 to 1, I have my f composed of sigma dotted with my derivative. And then my last C4, my f composed of sigma dotted with my derivative. And then the rest is calculation, algebra, and then I get that equal to 0, and taking the antiderivative, of course, the integral, and I get 0. I had mentioned I was going to do this parameterization a second way, which uses our opposite formula, and also it increases t. It keeps t going from 0 to 4, because sometimes actually in a physical modeling situation, you really just can't keep restarting t. So I'm going to call this the fancy way, but here we go. This parameterization starts out the same way. We notice on C1, y is held constant at 0, and if we let t go from 0 to 1, x can just follow t. Now, for the C2, we see that x is held at 1. T is going to go from 1 to 2. At this point, y can follow t, but we need to lag it by 1 second because now we've started t equal to 1. So this will keep our y lagging behind. So when t is equal to 1, y will start at 0. And then at the final point, when t is equal to 2, y will hit 1. You can plot some other points in between if you feel like you want the reassurance. Now for C3, the first thing we want to notice is that it's going opposite the direction of t. So essentially, we're going to use this formula to help us out here. So t is going from 2 to 3, and our formula says sigma of a plus b minus t. So that's 2 plus 3 minus t. So we get 5 minus t. But we also need to take into account that t starts at 2. So we want our x-coordinate to lag by 2. So that'll give us the 3 minus t. And then, of course, y is held constant at 1. Similarly, for C4, we're going to use a plus b minus t. That's 3 plus 4. That would be 7 minus t. But we need to lag y, in this case, by 3. So 4 minus 3, that we're back to 0 and 4 minus t. So that's our reparameterization, and I trust you can follow the rest of the steps. And you should get 0 to agree with our, when we did this problem the other way. Next, I have 5 examples for you, starting with this one here, where we have sigma is equal to sine t, cosine t, and t. That's the helix, right? It's a circle, but it keeps, as t goes, it moves up. And then t goes from 0 to 2 pi. And our f is just our radial vector field, so f of xy is just the vector xyz. Our first step has already been done for us. That's to parameterize the path. So I just wrote it out here. Sigma of t is equal to sine t, cosine t, t. And next, we want to write f in terms of our path. In other words, do the function composition. So f of x, y, z, I'm going to plug in sine of t for x, cosine of t for y, and t for z. And it's just equal to x, y, z. So I just get back sine t, cosine t, and t. And next, I take the derivative of the path. So derivative of sine is cosine, derivative of cosine is negative sine t, and derivative of t is 1. And now I can plug into my integral. So my formula here, I want my f composed of my sigma, which is right here, sine t, cosine t, and t. And then I want to dot it with my derivative of my path. So I'm dotting it with the derivative of my path. And again, I should have mentioned that I should always write this as part of my parameterization. T goes from 0 to 2 pi, so those are my limits of integration. And then I take the integral, plug everything in, and 2 pi squared will be my answer. My next problem will be to evaluate x squared, xy, and 1 over sigma, where sigma is given by t squared, and 1. My first step is to parameterize my path, which has already been done for me. So I go ahead and write that down. I have sigma of t is equal to t squared 1, t goes from 0 to 1. Also, just looking at this is the form of a parabola, right? It's because x is equal to y squared, and then we're just at z equals 1, at the height of z equals 1. So here's my parameterization. My second step is to write f in terms of my path, do the function composition. So f of sigma of t, so I plug in t for x, t squared for y, and 1 for z. And I'm looking at my f. And when I look at this f, I actually like to rewrite this as x squared, xy, and 1. I just have an easier time looking at it this way. So my first term is going to be x squared, which is t squared, and then x times y, so I get a t cubed, and then 1 at the end. Next, I take my derivative of my path. So derivative of t is 1, derivative of t squared is 2t, and derivative of 1 is 0. And then last, I'm going to plug into my integral. So here's my formula. F of composed of sigma of t is over here. T squared, t cubed, and 1. And then the derivative, my 1, 2t, 0. I dot them together. I get t squared. I get 2 t to the fourth, and I get 0 dt. I integrate, and this is my answer. The next problem is to evaluate the line integral of cosine z, e to the x, e to the y, where sigma of t is equal to 1, t, and e to the t goes from 0 to 0 to 2. So my first step is to parameterize the path, which has already been done for us. You know, this is so easy peasy when the path is done for you. It won't always be that way. Then the next step is to write f in terms of our path, the function composition, so f composed of t. So I'm going to plug in 1 for x, t for y, and e to the t for z. And then I rewrote my f just because I like looking at it this way. That's cosine of z for the x, e to the x for y, and e to the y for z. So my function composition is cosine of z, and z is e to the t, so that's cosine of e to the t. My next one is e to the x, so that's e to the 1. And then the last term is e to the y, so that will be e to the t. My next step is to take the derivative of my path, so that's just going to be 0, 1, and e to the t. And now I can plug into my integral, and my formula is here. I'm integrating from 0 to 2. I have my f of sigma of t here, cosine e to the t, e, and then e to the t, and I dot that with my derivative, 0, 1, e to the t. I dot my cosine e to the t with 0, and that gives me 0. I dot my e with 1, that will give me e, and then e to the t, I dot with e to the t, so that gives me e to the 2t. I integrate, plug in, and this is my final answer. Our next example is we're going to let sigma be the path cosine cubed theta, sine cubed theta, theta going between 0 and 2 pi, and we're going to integrate sine z dx plus cosine z dy minus xy to the 1/3 dz. I start by parameterizing my path, which has already been done for me, so I have cosine cubed theta, sine cubed theta, and theta between 0 and 2 pi. Then I write f in terms of my path. I do my function composition, so I'm going to plug in cosine cubed for x, sine cubed for y, and theta for z. And my f of x, y, z I rewrote, so that's sine z, cosine z, and minus xy to the 1/3. So doing my function composition, I need sine of z, which is theta. Thank goodness it's not sine of cosine cubed. That was going to be strange, but no, it's actually sine of theta, cosine of theta, and then the negative and the cube root of cosine cubed sine cubed, so I'm just left with cosine sine. The next step is to take the derivative of the path, so I have my sigma prime. Cosine cubed becomes minus 3 cosine squared sine of theta. The sine cubed becomes 3 sine squared cosine theta, and the theta becomes 1. And now I can plug into my integral using this formula from a to b. Oops, so that should be 0 to pi over 2. I'm so used to doing 2 pi, so you should watch that too. Pi over 2. And then I have my f of sigma of t. So that's my sine theta cosine theta minus cosine theta sine theta. And then my derivative, minus 3 cosine squared sine theta minus 3 sine squared cosine theta 1. From there, I've done my dot. I dotted sine theta times minus 3 cosine squared sine theta. I multiply my cosine theta times my 3 sine squared theta cosine theta. And then I have my cosine theta sine theta. There's probably a lot of simplifications with the sines and cosines, but here is the rest of my integral and calculations. And just one final note, this negative sign here means that the field resists movement along the path in that direction. My last example, f, is the vector field x cubed yz, and the path is a circle of radius a in the yz plane. So this one we actually have to parameterize. Yay! Here I have my parameterization. Since it's in the xz plane, in the yz plane, that's where x is equal to 0. And then my radius is a, so I have a cosine theta, a sine theta. Theta goes between 0 and 2 pi. You're going to be parameterizing so many circles and maybe a helix. It's good to know this. My next step is to write f in terms of my path, do the function composition. So f of sigma of t, so I have my x cubed, which is just 0, my y, which is a cosine theta, and my z, a sine theta. And then I take the derivative of my path, so that's just 0 minus a sine theta, a cosine theta, and then I plug into my integral using this formula here, a to b, that's 0 to 2 pi. My f of sigma of t is here dotted with my derivative. And if you look at this, it looks like it's going to cancel out. When we do the calculation, the dot product, we see it's equal to 0. And if we also look at this kind of pictorially, we have this circle, and f is radially out. In other words, it has this x component, which is extra long, but it's basically x, y, and z. It's pointing outwards from the center. And so since f is radially out, it is perpendicular to the circle, meaning the work done is equal to 0 along this circle, which is exactly what the 0 is. And this last example is about Tom Sawyer's Ant's Fence. And I don't know why, but every vector calc book I've seen has a variation of this. Maybe the function f of the height of the fence is different, or it might be the parameterization of the fence is different, this line. But everyone talks about Tom Sawyer's Fence. I'm not sure why, so I included this here. And the Tom Sawyer's Fence comes from the book by Mark Twain, Tom Sawyer. And in the story, Tom Sawyer's aunt punishes him by making him repaint the fence. But while he's painting, some other kids come along and ask what he's doing, and he makes it sound like painting the fence is like a ton of fun. And then his friends come and ask, well, can I help? And he says, well, I don't know. It's a lot of fun, and I don't know if I want to share. And then they beg him, and so he agrees to let them help him paint the fence, but they have to pay him. And so that's kind of the story of Tom Sawyer. And essentially, this question's asking you if he's going to estimate how much he can get for every foot of fence he can do, and they're willing to pay him this much money, how much can he hope to earn? To figure out how many square fence he has, we're going to figure out the length of the fence using the parameterization of the fence in the first quadrant, and then we multiply by the height, which is given here. So we start again by putting everything in terms of sigma. And again, I should also mention this is a path integral because this height is a scalar. So f of sigma of t, so f of, and our sigma is 30 cosine cubed and 30 sine cubed, is equal to 1 plus, and then 1/3 of the y term is 10 sine of t. I also take my derivative of my path, so I get 90 cosine squared t sine t and 90 sine squared t cosine t. I take the length of this integral because now it's a path integral. I need to multiply by the magnitude, and that's 30 sine cosine t. So my integral is from 0 to 2 pi because I'm given my parameterization 0 to pi over 2. Sorry, not 2 pi, but pi over 2. I have my f of t and my sigma derivative, the magnitude of that here, and I just moved the 90 outside. And now I can perform my integration, plug in my limits of integration, and this is my final answer. To review what we've done, we looked at path integrals both for scalar and vector functions. And the path integral, we have these two formulas. This is for scalar functions, little f, when f produces a scalar. And this is for vector function, capital F, when capital F produces a vector. We said there were 3 steps to do these line integrals. First is to parameterize the path. Second is to write our little f or big F in terms of the path, and we use function composition. And we do this because we're only interested in the field along the path. We take the derivative of the path, and for scalar functions, for little f, we also take the magnitude of the derivative to plug in here. And then last, we plug in all these components into our formulas. So the first example we did was a path integral of a scalar function. So here we have a path. Sigma goes from sigma of t, it's parameterized by t goes from 0 to 2 pi, and sigma is equal to cosine of t, sine t, and t. So it's this helix. It's this circle that keeps rising. Our function that we want to integrate over the path is x squared plus y squared plus z squared. This is a scalar function. So we're going to evaluate the path integral of f over our path. So the step one is to parameterize our path, which has already been done for us. Sigma takes t and it produces cosine t, sine t, and t. Step two, write f in terms of the path using function composition. So f of sigma, so we're just going to plug sigma into here. So that's cosine t, sine t, and t, and then we're going to plug cosine t, sine t, and t into f. So f is x squared, which is cosine squared, plus y squared, which is sine squared, plus z squared, which is t squared. So we get 1 plus t. The third step, take the derivative of the path. So here's our path. The derivative is derivative of cosine is negative sine, derivative of sine is cosine, derivative of t is 1. And since this is a scalar, here it is. For scalar functions, we find the magnitude of the derivative. So we take the magnitude of this and we get square root of 2. And finally, we can plug everything into our formula. For our scalar functions, that'll be f integral from a to b. Here, a is 0, b is 2 pi, the integral from 0 to 2 pi. F composed of sigma, so that we had written f composed of sigma is 1 plus t squared, and then times the magnitude of sigma squared, which is square root of 2, and then we can integrate and find our final answer. For a vector function, we can also do path integrals, and this is our formula, which I rewrote here. So our example, same path, sigma sine of t, cosine t goes between 0 and 2 pi. Our vector function now takes x, y, and z, and it's the identity function. It just gives us back x, y, and z. So we compute the line integral of f over sigma. Step 1, parameterize the path, which has been done for us. Step 2, compose f with our path. So f composed of sigma. So into f, we're going to plug in sigma, which is sine t, cosine t, and t. So f gives us for the first coordinate x, so that's just sine t. Second coordinate, we just plug in y, which is cosine t. Third coordinate will be t. Step 3 is to take the derivative of the path. So again, derivative of sine t is cosine t, derivative of cosine t is negative sine t, derivative of t is equal to 1. And finally, we can plug in the integral. So here is our formula. So integral from a to b, that's 0 to 2 pi, given here. F composed of sigma, we have calculated as sigma t cosine t, dotted with the derivative, which is cosine t negative sine t 1, and then we do that integral and we find our final answer. We talked about reparameterizations of a path. So sometimes we can have, first the line integral depends not only on the field but also on the path. Obviously, if you look at the formula, the path is in the formula. In general, two different paths will yield two different values, but if the path integral is the same with a possible exception of a change of sign, then we call that a reparameterization of the path. And one reparameterization is we looked at the orientation reversing parameterization, and we have this theorem that said if it was orientation reversing, the line integrals would be the same, except we would have a negative sign. I'm going to skip a little bit ahead. We also talked about the path integral of a vector function as work done. So we can interpret this path integral as work done by a force moving a particle along a path. We also saw this alternative form, which told us that it was the component of f that is in the direction of sigma along the path that helps the work done. I'm going to come back up here to talk about reparameterization of a path. You can have an orientation reversing parameterization, which we had seen in the video and also I talked about on the previous slide. But also we had this here, these two examples here, which I wanted to talk about. We have x equals cosine 2t, y equals sine 2t, for t goes between 0 and pi. And we said that was a reparameterization of x equals cosine of t, y equals sine of t, when t goes from 0 to 2 pi. We saw that both of these trace out a circle once. It's just that this traces it out in half the time because of this 2t. So we only have to wait for time to go to pi rather than here, time to go to 2 pi. But the work done is the same. Work done doesn't depend on speed. So these two will give you the same, they're considered the same paths and just reparameterizations. Whereas here, when we look at x equals cosine t, y equals sine t, when we go for t equals 0 to 4 pi, this is not considered a reparameterization of x equals cosine t, y equals sine t, t goes from 0 to 2 pi. Again, they trace out the same circle. It's just that this traces it out twice. And if you think about it, the work to move around a particle, a circle twice, is not going to be the same as moving it around once. So even this traces it out twice, so it's not considered the same parameterization. For review, I have 5 problems for you to try. The first one is let little f of x, it's a scalar function, equal x minus y, and let x go from 0 to 3 to r2. So that's going to be a planar path. And x of t, our path, is given by 2t comma t for t between 0 and 1, and t plus 1, 5 minus 4t, if t is time is between 1 and 3. So we want to evaluate this little f, the path integral of little f over this path x. The second problem, let big F, this is a scalar function, equal x, y, z, the radial one which we have seen, and let x be the path going from 0, 1 to r3, and it's the path x of t goes from, is given by x of t is given by t, 3t squared, 2t to the third. So we want to evaluate the line integral of capital F along the path x. The third problem, another vector field, so capital F of x, y. Compute the work done moving along the circle x squared plus y squared equals 9, which may be parameterized by x equals 3 cosine t, y equals 3 sine t, t goes between 0 and 2 pi. We want to use the tangential method to show that no work is done. And B, compute the work done by f equals y minus 2x, so this different vector field. The fourth problem, compute the line integral over the path x plus y dx plus x plus z dy plus x plus y dz, where x is the path, x of t is given by t squared, t to the third, for t between 0 and 1. The last problem, calculate work done by f, another vector field, equals x minus y, x plus y plus z, on the particle moving along the parabola y equals 3x squared, z equals 0, from the point 0, 0, 0 to the point 2, 12, 0. I suggest you pause the video, give the problems a try, and then I'll have solutions for you. This is the solution for the first problem, including a graph of my path. This is the solution of the second problem. And finally, solutions for my fourth and fifth problem. And that is it for this video. Thank you for watching.